Welcome to the CEDAR virtual workshop presentation. My name is Nicholas Lee, and I'm a research engineer at Stanford University. I will be talking about a CEDAR-funded project entitled Atmospheric Neutral Density Dynamics through Meteor Observations. Our principal investigator on this project is Professor Sigrid Close. I want to start with a brief overview of meteoroids and plasmas. Meteoroids are naturally occurring solid bodies in space that can range from dust-sized particles that are tens of microns in diameter up through about a meter in size. Meteoroids encounter and interact with plasmas throughout their lifetime. This includes interactions with solar wind resulting in a surface charge that changes their orbital trajectory, as well as interaction with neutral gases as they encounter planetary atmospheres leading to ablation of the meteoroid and forming meteor plasma. Meteoroids can also encounter airless bodies or spacecraft, resulting in shock-induced ionization and production of highly dense plasmas. What we're focused on today are meteoroids that enter the Earth's atmosphere, which provides a source of extraterrestrial metallic ions deposited into the atmosphere itself, and also provides a probe that can allow us to infer the atmospheric conditions being traversed. One big question that our research group has been focused on is what is coming into the Earth's system, and what is it passing through? This project in particular deals with a new technique that can be used to determine what neutral density in the atmosphere these meteoroids are encountering. The neutral density of atmosphere can be difficult to measure directly at the MLT altitudes. Space-based in situ measurements go down to about 360 kilometers, and balloons can only go up to about 30 kilometers. In between, what we depend on are inferred measurements from remote sensing. Prior meteor-based measurements rely on ambipolar diffusion models, and incoherent scatter radar techniques have been developed that depend on ion-neutral collision frequencies. The atmospheric neutral density exhibits dynamics that we don't fully understand, and these can be major forcing functions, leading to enhanced density at higher altitudes. For example, models predict low-density cells at high latitudes, and seasonal variations such as those reported at lower altitudes can drive zonal winds that we haven't fully characterized. What we plan to do is to use meteoroids as a probe into the atmosphere. Interplanetary meteoroids enter the Earth's atmosphere at between 11 and 73 kilometers per second. This speed range is based on the Earth escape velocity for the lower bound and heliocentric escape velocity mapped to the Earth frame for the upper bound. As meteoroids enter the atmosphere, they ablate because of the heat resulting from their collision with neutral molecules. This results in energetic collisions that ionize the neutrals, forming a plasma typically between 80 to 100 kilometers altitude. This plasma is composed of two parts, the head plasma that moves with the meteoroid and the trail that is left behind in its wake. At the bottom you can see a radar range time intensity or RTI plot. Time is the x-axis and range is the y-axis, so each vertical line here is a single radar pulse. At the left you can see the streak corresponding to a meteor head echo, and on the right the meteor trail is evident. This was a radar measurement that was collected at Hikamarka Radio Observatory by Ryan Volz, one of our former students, back in 2014. Our project builds on some of Ryan's PhD work where he looked at optimizing radar waveforms for incoherent sampling. This allows us to apply compressed sensing techniques to process the meteor head signal by leveraging the fact that the RTI should be sparse. Ryan showed that this technique can increase the range resolution of the meteor measurement, allowing us to obtain very precise trajectories. We're exploring ways to make this more computationally efficient so that it can be implemented to process meteor trajectories in real time. This project also builds on another student's work. Alan Lee, who graduated in 2016, demonstrated using radar trajectories of meteors from Altair to infer atmospheric neutral density. Altair is a high-power large aperture, or HPLA, radar facility. These typically use higher frequencies and narrower beams than dedicated meteor radar facilities. Alan's technique was to track the head plasma of the meteor to determine the deceleration of the meteoroid subject to drag and ablation. These two effects can be combined into a single equation where all of the meteoroid unknowns, including the drag and ablation coefficient and the heat of enthalpy, can be lumped into a single parameter. This difference equation then relates the meteoroid speed and acceleration at 2 points in time to the atmospheric density at those points. Now, if we define a fixed set of altitude layers and make pairwise comparisons of a single meteor as it traverses these layers, we can lump the differences into elements that will populate a matrix equation. Multiple meteors traversing the same altitude layers will add to the matrix equation, leading to an overdefined system that can be inverted to solve for the ratio of atmospheric densities between layers, as well as the lumped meteoroid parameters. We can then pose this as a convex optimization problem where we're minimizing the norm of a matrix expression subject to the meteoroid parameters being positive. From the batch meteor data over a short period of time, we can estimate the atmospheric neutral density profile over the altitude range of interest. If we have knowledge of the source meteoroid population, we can apply statistical techniques to pin this relative density profile to an absolute profile based on the simultaneously estimated meteoroid parameters. Allen demonstrated with the Altair data that this technique could predict variations in neutral density that are correlated with changes in solar conditions. So building from Ryan and Allen's work, what we did this past year was a coordinated experimental campaign to collect meteor data that we can use to study the latitudinal coupling in neutral densities. We used 3 HPLA facilities at similar longitude, but which spanned from Hikamarka in the equatorial region to Millstone Hill at mid-latitude and to Riser up in the polar region. The coordinated collect, which we did on October 10th and 11th last year over 4 hours each day, we believe is the first dedicated meteor collect to be simultaneously undertaken across 3 facilities, which also gives us useful information on the differences between the facilities and what they see. We initially planned to collect data at all facilities across 2 weeks on the 17th and 18th as well. This was done at Riser, but Millstone Hill experienced a power outage, and Hikamarka required too much setup and configuration time to dedicate multiple collects separated by a few days. But because Hikamarka was dedicated to this experiment over the days we were operating, we ended up collecting 8 hours per day rather than 4. At Riser and Hikamarka, we used a minimum side lobe 51 baud code with 1 microsecond baud rate, but to preserve code fidelity at Millstone Hill, we went with a slower 6 microsecond Barker 7 code. The interpulse period ranged from 1.25 to 2 milliseconds, and sample rates were 1 to 2 megahertz, giving us a range resolution of 75 to 150 meters. We also tested an experimental 25 megahertz sample rate for a short time at Millstone Hill, which gives us an opportunity to test new signal processing techniques to get improved deceleration profiles. Looking at the detection rates, we had about 1 to 2 meteors per minute detected at Hikamarka on October 10th, with a peak in the early morning. As we hit sunrise, the daytime electrojet obscures meteors and our detection rate falls to 0. On the same day, Riser had an overall detection rate that was similar to Hikamarka. There wasn't a clear diurnal trend in the polar regions, with a detection rate that is fairly consistent across the 4 hours of data collection. This ended up averaging just under 1 meteor per minute that had a strong enough signal where we could try to compute a deceleration profile. Now, if we expand the plot to zoom in on the 4 hours where Riser was active, and plot the counts from the other 3 days when we took data, the meteor detection rate at Riser looks relatively consistent. This repeatability is indicative that we should be able to apply the same population statistics on these meteors across multiple days. Looking at an individual meteor, this is an example of one seen at Riser, where the RTI signature of the head echo is smeared in range because of our long pulse that we're using for high sensitivity. Our initial step was to use a matched filter with no Doppler shift to enhance the signal-to-noise ratio. This was used in an automated meteor detection algorithm to look for meteor-like events, but because the return signal from a moving meteor is Doppler shifted, we're left with some ringing around the pulse peak. So what I did in terms of looking for a computationally efficient technique to pull out a high precision range rate was to apply a second matched filter to this signal from a sample pulse in the middle of the meteor streak. This sidestepped the need to synthesize a bank of Doppler-shifted matched filters by using the received signal itself as a template in order to clean up the residual ringing. What that gives us is a very tight pulse centered on the meteor trajectory, and then instead of just looking for the peak value, I compute a weighted average of the pulse power to avoid being constrained by the range resolution derived from the sample rate. So on this slide, you can see how the computed trajectory in red superimposed on top of the original pulse, showing how they line up. Looking at the overall populations, one thing that is important to note is that the polar meteors detected at Riser have a much faster mean and median speed compared to the equatorial meteors seen at Hikumarka. So in terms of using our overall meteoroid statistics to pin an absolute density profile, we will likely have to build unique meteoroid population statistics for each facility and consider selection effects from the geographic location, beam direction, and frequency of each radar. So to conclude, the project that we're working on is moving towards meteor-derived atmospheric density measurements. What we're hoping to ultimately do is to provide a technique that can be used for continuous monitoring of atmospheric neutral density at the 100-kilometer altitude range, using existing facilities that can also complement measurements of other atmospheric parameters. What we've done so far is what we believe to be the first coordinated HPLA meteor radar campaign that allows us to look at the differences in meteoroid population, as well as the detection rates that are achievable from different latitudes. These measurements won't only support the current program that we're working on, but will also enable future studies into plasma dynamics that are associated with the meteor heads and trails. The next steps for our projects are to take the meteors that we detected and refine the trajectories to obtain deceleration profiles. We then need to take these deceleration measurements and perform the convex optimization step to invert the measurements into a neutral density profile in order to look for density structures that we wouldn't be able to see with other techniques. Given the statistics we have, we're hoping to track the evolution of these density profiles as they evolve over the period of observation. My eventual goal is to turn this technique into a Bayesian estimation process that allows us to continually feed new meteor detections into a continuously updating estimate of the neutral density of the atmosphere over time. Before I wrap up, I do want to highlight the students that have been involved in this project. Diana Juarez Madera had prior experience working with Riser for a GEM project looking at electron precipitation, and applied this experience to coordinate the radar campaign for this project. Yifeng Chang is a master's student who was involved in porting some of our prior radar code into a form where I was able to use it to work with all the new meteor data we collected. Coming up, Jared Blanchard is a new student who's been looking at some orbital mechanics work with JPL and is interested in applying this work to look at meteoroid orbit selection effects that would feed into our population parameters for the different radar facilities. And Trevor Hedges has not been directly associated with this project, but he's interested in building up our plasma simulation capability to study the meteor plasma dynamics, so the radar that we're collecting here will support his research as well. I also want to thank NSF for supporting this project, as well as the many staff members and scientists at the 3 radar facilities who supported our campaign. Marco and Karim invited me out to Hikumarka to be on site during this campaign. Phil and Ryan at Millstone Hill were very helpful not only in collecting this data for this experiment, but Ryan's PhD work motivates a lot of what we're doing now. And finally, Roger Varney at SRI facilitated our Riser collect. If you have any questions or feedback on this talk, please contact us at the emails listed here. Professor Sigrid Close can be reached at sigridc@stanford.edu, and I can be reached at nnlee@stanford.edu. Thank you very much for your time.